Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Yes, hello my wonderful students. I believe you're fine. I'm also doing fine. I am happy. I expect you also to be happy amid some challenges that you may be facing, because everybody has a challenge. So I want to take this time to welcome you to this session of TV learning, and I thank you for being attentive always. I am sure you are going to be, because it's a common routine, you are going to have your calculator, you are going to have your notebook, and you are going to have your pen and pencil and maybe a math set, because we shall need to be drawing some diagrams and also making some calculations. My name is Teacher JB, a friend of Senior 2 physics students. That means I'm going to be with the students of Senior 2 for today. And so, Senior 2s, you know very well, we are looking at unit number 6. I have some friends who do sign language. They told me sometimes you can demonstrate 6 like this. I don't know whether that's true. So we are looking at unit number 6. And what does it say? It is Pascal's principle and its applications. That's what we have been looking at. And every time, remember, I told you I will be reminding you to remember the key unit competence. That is, you as a learner, you should be able to explain transmission of pressure in fluids at rest and describe its applications. And for us today, we are looking at lesson number what? Number 5. The last time we were here, we were looking at lesson number 4. Now this is lesson number 5. And lesson number 5 is about the hydrostatic paradox. Those are big words, right? Especially paradox. Paradox. So paradox, that's a word that confuses many people. You can go and check also in the dictionary and see, English dictionary, and see what paradox means. But in my understanding, a paradox is something that happens and you do not expect it to happen like that. Like, kind of contrary to common belief. There are the things that happen like that, contrary to common belief. You expect something to happen in a certain way, and then the reality is that it happens in a way which is opposite to what you expect. And hydrostatic, remember, we talked about this before. Hydro normally refers to water, and static normally refers to no motion, a body which is not in motion, something which is not moving. Like right now, my state is static. So that is what we are going to be looking at. In relation to liquids or water and pressure, we will look at the hydrostatic paradox. In terms of pressure, then these liquids or water behave in a certain way that when you look at it on first sight, you don't expect it to behave that way. So we are going to be looking at the hydrostatic paradox. So our learning objectives for today are only 2, which is 1, we need to explain the hydrostatic paradox. And then 2, we should be able to solve some numerical problems that is related to hydrostatic pressure. And I'm sure this is not going to be a big challenge to us, because Unit 5 and Unit 6 are closely related. Remember, Unit 5, we are looking at pressure in liquids, pressure in fluids. And Unit 6, we are looking at Pascal's principle. And Pascal's principle, remember, deals with transmission of pressure in fluids. So you'll see there's a very close connection between those two. Now, let's begin off with this question. I had intended to give you this question last time, but we didn't have enough time, so we need to complete it. And so let's read the question together. Find the pressure needed to push or pump. You can even use that word, pump. Find the pressure needed to pump water to the top of the water tower. Remember last time we were talking about a water tower. So this is our question 2. And I'm going to put a sketch, okay, so that our question comes alive. We have got a water tower. The tank is constructed, it is something like this. That is what you see on your diagram. And then, of course, it has some stands to keep it firm without collapsing. So that is what you have in my simple sketch. Okay? So this is the tank or the water tower. You remember that? We looked at water tower last time. So this one is our water tower. Okay? So it means inside there is water. And as you can see from the screen, water is coming out of the tank, like here. Water is coming out. So we are saying this is water. Okay, let me not go so much into that. So what have we been asked to do? They are asking us to find the pressure. So again, as I told you, if you cannot summarize the details, it means you have not understood the question. So what have we been given in this question? They are asking us to find the pressure, and pressure is represented by letter P. Required to push or to pump water to the top of the tower, a height of 18 meters. So it means the height of this tower is 18 meters from the ground. So here I'm going to have H, which is 18 meters. I don't need to change this because it is a standard unit, so no problem. From the ground, if the density of water is 1.0, so we have got density of water, which is 1.0 grams per centimeters cubed. I have a problem here. You should have a problem there as well, because this is not a standard unit, grams per centimeters cubed. This is meters. So it means our density also must have meters in it. So we need to change this from grams per centimeters cubed. We now need to change it into kilograms per meters cubed. That's the problem I have there. So we need to change it up. So changing this and up means we multiply this by 1,000. Remember, we looked at that before. So this one becomes 1,000 kilograms per meters cubed. So that is our density. Then, there's something we are being told. Assume sea level conditions. So this experiment, this water tower is at the sea level. So because it is at the sea level, then we should get atmospheric pressure at sea level. Do you remember we talked about atmospheric pressure at sea level? Yes. The atmospheric pressure at sea level is approximately 1.0 times 10 to power what? 5 Pascal. That is the atmospheric pressure at sea level. So all these have been given. So is it okay for us now to calculate the pressure which we need? Yes. Now the reasoning here is this, and I need you to understand this very well. Atmospheric pressure, because you have water, let's say you have water somewhere here, okay? This is the water you have. Now, you need to pump this water to go to the tank. So for you to pump the water, take the water to the tank, okay, water must attain a pressure equivalent to this height of 18 meters. But because this is atmosphere, you see the space here, this is atmosphere. And there's atmospheric pressure. Atmospheric pressure is pushing this one where? Down. So it means the pressure which we need is, first of all, the pressure which is used to overcome atmospheric pressure. After overcoming atmospheric pressure, then now we need the pressure that the water will use to move up to a height of 18 meters. In other words, the pressure we need is a summation of how many pressures? 2 pressures. Do you get that? Let me take you to force. We can try to understand this using force. Let's have this idea. Just imagine, okay, imagine you have a slope, and this is your car on the slope. Just take that as a car. Doesn't look like a car, but just take it as a car. So this is a car, which is on the slope. Now, you want the car to move up. Maybe the engine of the car has failed. And if the engine of the car has failed, this car is most likely to go down. So, if I want the car to move up using a certain force, I first of all say the weight of the car is pulling the car backwards. So let us say it is pulling the car backwards using a force of what? 200 newtons. So if you want this car to move up, you have to push, okay? Let me use another color. You have to push the car using a force. So your force that we are talking about must be here. So you have to push the car upwards. Now, if you push the car using a force of 50 newtons, just imagine 50 newtons. Do you think the car will move up? No, it won't. Because this force is bigger. So 50 newtons, no. If you push it using a force of 200 newtons, will the car move up? Again, I'm saying, no. The car won't move because they are now the same. If I push it with a force of 300 newtons, will the car move up? Yes. Why? Because 300 newtons minus 200 newtons gives us an extra force of how many newtons? 100 newtons upwards. You get the idea? So that's why the force which you are applying to overcome this must be more than what? 200. You get the idea? It must be more than 200. So in the same way, atmospheric pressure is acting downwards. So if we have to push the water, pump the water up to here, we must give it a pressure which is first of all more than the atmospheric what? Pressure. More than the atmospheric pressure by which height? By this one. So we now come and say the total pressure which is required, total pressure is P, is going to be equal to the atmospheric pressure then plus the pressure due to this height of water, which is going to be rho g h. Okay? And so when we come to the atmospheric pressure, it is 1.0 times 10 to the power 5. Everybody knows it is 100,000 Pascal, then plus rho, which is density of water, 1,000, times g, which is 10, times h, which is 18. So get the connection between this and what we have said here. Very practical. Very practical. And so let us get what this one means. Remember, I told you to get your calculator. Much as that may be a bit easy for you to even use your calculator. But you can get your calculator and try to find it out. We have got 10,000 times 18. That becomes 18,000. Okay? Then plus 1.0 times 10 to the power 5, which I've simplified to 100,000. So we shall add that one to 100,000. And when you add it, it is going to give you 118,000. And because all the units are standard, then we shall also use a standard unit of pressure, which becomes 118,000 pascals. As easy as that. Hopefully you have seen why we have been able to convert those different units. So I'm giving you a few seconds to just finish writing that one up before we look at question number 3. Okay? You have your nice diagram, you have your nice formulas, you have written, everything is fantastic, I want to believe. Question number 3. Now, question number 3 is about swimming. Do you love swimming? Me, I love swimming. I used to swim when I was still young. and I stayed for a long time without swimming. The last time I tried swimming was last year, and I was sinking into the water. But after practicing for a few minutes, I was able to swim very nicely. And so, don't go to a swimming pool if you do not know how to swim, okay? Because swimming pools can kill, water can kill if you do not know how to swim. So in Kigali, for some of you who are going to Kigali, even other cities in Rwanda, you see there are so many swimming pools. So you have a swimming pool that measures 18 meters by 10 meters, and it is 2 meters deep. So let me just try to sketch that swimming pool. The swimming pool could be like this. The way it is in the form of a rectangle. So you have this as a sketch of the swimming pool. And of course we know it is full of what? Full of water. That is our swimming, how it is looking like. So it measures 18 meters by 10 meters. So let me use another color here. Let me say this is 18 meters, which is also this one. I can put it down here, 18 meters. I've not drawn to scale, okay? Not drawn to scale. Okay, so let this be 18 meters, and let that be, even if I've not drawn it to scale, we should try to make it at least look like the real thing. So allow me change it a little bit. We are not measuring, but it should be realistic. Okay, should look realistic. So let this one be 10 meters, and let this be 18 meters, and they're telling us it is 2 meters deep. That means the depth is 2 meters. That is more realistic, but still, remember, it is not drawn to scale. So you don't need to measure. Right. They're saying, what is the pressure at the bottom of the pool? And remember, they're telling us it is on average. Look at your screen. 2 meters deep on average. The normal construction of a pool is not like this. A pool is constructed like this. This is how it is constructed. So that this side here is shallow. And this side here is what? Is deep. That is how the pool is constructed. So for you guys who are a bit short, I'm very sure all students of Senior 2 are a bit short. Okay, maybe some people are taller than me, you never know. It is better if you go to the swimming pool, you stay around here because this side is deeper. But now we are looking at average. The average is about 2 meters. So what is part A asking us to do? Part A is asking, what is the pressure at the bottom of the pool? So they want the pressure at the bottom of the pool, here. So pressure at the bottom of the pool is a result of two pressures. Because remember, there's atmospheric pressure above this pool. Even when you look at your diagram, you see, there's pressure above this water. You see, a beautiful swimming pool in Kigali. There's atmospheric pressure above the pool. So the total pressure is going to be atmospheric pressure, then plus the pressure due to what? Due to the water. I'm going to put it like this. Pressure due to water. So we need to add those two. And so atmospheric pressure 1.0 times 10 to power 5. Pressure due to the water, remember, is given as rho GH. And rho is 1,000 times G, which is 10, times H. The depth there is 2 meters. And so this is going to give you 100,000, then plus. This is 10,000 times 2, which becomes 20,000. And so that gives you 120,000. And that is going to be in Pascal. So that is part A. Part B, what is the force exerted by the water in the pool on the base? So they want us to get the force. And remember, force is equal to pressure, then times the what? The area. Now, the total pressure being exerted is 120,000. So what do we need to do? we need to get the area. Okay? We need to get the area of the bottom. And getting area of the bottom, I believe that is very easy, because area of the bottom is going to be this. Area of the bottom, which is going to be 10 times what? 18. And I want to believe you can find out that nicely. Remember, those are some of the calculations we have carried forward from unit number 5. So let me go to the hydrostatic paradox. And hydrostatic paradox, I'm going to explain it using the diagrams we have on the screen. Now, look at the diagrams you have on the screen. Beginning with the first diagram, look at the 2 points, A and point B. Point A and point B. What point do you think should have a greater pressure? When you just look at it, automatically you can think that the point which has a greater pressure is point what? Is point B. Because point B appears to be carrying more water on this, above it. You can see, because here you have got more water, then this one is just a slender amount of water. You would be forgiven to think like that. But you know what? The truth is, the pressure at A is exactly the same as the pressure at what? At B. Why? Because the hydrostatic pressure at the bottom of a liquid column is proportional to the height of the liquid and not the volume of the liquid in the what? In the container. That is the hydrostatic paradox we are talking about. That the pressure, which is okay, hydrostatic pressure at the bottom of a liquid column only depends on the what? Mark this word. Only depends on the height, but does not depend on the volume of the liquid which is found in the container. So that is something very important that you must remember. And that's why when you look at all these shapes, the pressure at A is the same as the pressure at B. And so we only consider this column of water above the area where you have got B. Do you see this column with the dotted lines? That is what we only concentrate on, because they're saying the pressure does not depend on the volume of the liquid, but rather on the height of the liquid. In a similar way, the pressure also, if you look at this container where we have written B, the pressure at the bottom is only due to the height from this point up to the surface of the liquid. It is not affected by this, part 3 or part 1. In a similar way, it is also the same here. Pressure at 1, 2, and 3 are going to be the same because we are only looking at the height here, okay? And the same thing happens to D. Even when you look at container E, the pressure here at the bottom, here, is as a result of the 3 heights. This height, that, and the other one. So the hydrostatic paradox tells us the hydrostatic pressure at the bottom of a liquid column is proportional to the height of the liquid and not the what? Not the volume of the liquid in the container. Okay, look at that question 4. They are asking us to rank the pressure at the 3 points in that figure. The pressures at the 3 points. Pressure at A, B, and C. So do you think the pressures are the same? Automatically, no. Pressure at A is less than the pressure at B and also less than the pressure at C. But according to me in this diagram, pressure at B and C, okay, B and C are the same level. So what does it mean? Pressure at B is equal to pressure at what? At C. So that means B, C, and D are automatically wrong. So pressure at A, yes, is less than pressure at B. But pressure at B is equal to pressure at C. So our answer in that case is A. Okay? Then, lastly, for today, they are asking us to calculate the pressure due to water column of height 100 meters. So what is the pressure due to the water column? That is our question 5. Pressure due to the water column. So that is the pressure due to the water column. Remember, pressure is rho GH. And then density of water is 1,000 times G, which is 10, and then times H, which is what? 100. Because they're telling us it is 100 meters. Are you seeing that well? 100 meters. G is given, density of water is given as 10 to power 3. Let me use another color. Now, density is 10 to power 3, kilogram per meters cubed. But now if it is 10 to power 3, remember, it is 1,000. G is given as 10 newtons per kilogram. Okay? Or even meters per second squared, not a problem. So in that case, this is going to give you 1 million. 1 million. And then the unit is going to be Pascal. So if you have got 100 meters of water, that is the pressure you're going to have. Now, what is the height of the mercury column? That will exert the same pressure. So let me call this one part 1, then this is part 2. So same pressure, remember we are using pressure is rho GH. And if we want to get the same pressure, so it becomes 1 million also, is equal to rho, which is density of mercury. Density of mercury is 13.6 times 10 to power 3, then times G, which is 10, then times H. So the only thing we need to do is to get H. So H is now going to be equal to 1 million, okay, 1 million divided by, remember this is 10 to power 1. So it means divided by 13.6 times 10 to power 4. I'm very sure every one of you is able to calculate H. I'm also going to calculate it so that we can compare the answer. And so for today, I'm going to leave you with exercise, which is question number 6. Make sure you go through question number 6 and then find the answer. So very quickly, as I conclude the lesson, we just press this figure to find the answer, and then while you are looking at your assignment for today. So I have 1 million, okay, then divided by 13.6, then exponent 4. Yes, exponent 4. So I'm coming out with this answer, that H is equal to 7.35. Remember, all the units are standard. And because all the units are standard, that H is going to be 7.35 meters. Did you get that? If you got that, congratulations. And so, thank you so much, my wonderful students. I know you have been able to follow through this lesson. We have met our lesson objectives, and we have been able to, I believe, understand the concepts that we have explained. Thank you so much for being good students. I leave you with that assignment. Do it so that next time when we meet, we shall start with that number and see the corrections. Thank you so much. Bye-bye.